resonance. Unfortunately, it's an empty room.
Before and
Before.
implementation of this.
Right. Oh. None of the students are here. I know you are. Most of them. It's empty. Ah, yeah, I see.
They will walk in. Just give 2 minutes.
Okay. पता है मुझे कल आपको दिक्कत थी. Yeah. Okay, I am going to start formally the colloquium. So I would like to thank our speaker, Professor Michael Dozer. We are thankful that you're here for actually physically giving the talk after the series had been hit because outside visitors would not be able to come. But now since things have much better for travel, and I'm happy that you're here. So thank you for coming by. Before I start the colloquium today, I would like to sort of remind those who are joining for the first time through YouTube. So this colloquium is on YouTube as well as Zoom. That the Wednesday colloquium series is pretty historical for us because it has been part of a tradition that was started by our founding director, Professor Homi Bhabha, who would come once on a Wednesday to the institute, visit the institute, and meet with all the faculty members here, and also host this colloquium because it was sort of a way to bring visitors to TIFR. And the idea was to actually gather all the faculty from natural sciences, physics, chemistry, biology, together and listen to the speaker so that not only there would be sort of ideas generated during the talk, but also after the talk, allowing, even within intra-departmental collaboration to prosper. So this is a very good idea. It has benefited the students, and I'm thankful this is continuing. And so before any further delay, I request Professor Rajdeep Chatterjee, who is our new recruit in the institute, to kindly introduce Professor Dozer. Yeah.
Thanks. It's a real pleasure to introduce Michael Dozer to all of you. He's a senior research physicist at CERN and also serves as a spokesperson for the AGES experiment. He's an editor of several journals, including Physics Letters B. He specializes in working with antimatter for the purposes of formation of anti-atoms, studying matter-antimatter asymmetry, among other uses. He uses it either as a tool or as an object of study itself. More recently, he has also been closely involved in exploring application of quantum sensors to particle physics. He has other activities that he does other than physics. He has been a founder of the Board of Arts and organizes lectures for wide audiences, and has been involved in defining the program for TEDx and CERN and other stuff. But there's a closer connection Michael has with TIFR that I recently realized. He's sort of our next door neighbor. It turns out that the TIFR office at CERN is right next to Michael's office. And when we were students doing our PhD there, we would see a nice poster stuck that, "Don't worry, put it on Michael's budget code." And if you know at CERN, for anything, even if it's free, like you want to rent a bicycle, which is free, you need a budget code. So Michael, if that offer is still valid, I would take you up on it. Thank you.
Okay, now you've set me up for failure. Thank you for the opportunity. It's a great pleasure to give a presentation here, and there seems to be some kind of echo.
Yeah.
Just let me see. I don't think I can fix that from here.
No, he will.
Yes, exactly. I will keep talking, and yes, there we go. Perfect. Okay. So great pleasure to be able to give you a seminar in person, as you pointed out before. It's also a great opportunity to talk about something interdisciplinary, which is really the role that quantum sensors can play in particle physics. And you'll see this goes well beyond high energy particle physics into all domains that are related. I'll be talking about quantum sensors for both high and low energy particle physics.
Maybe just touch the screen there.
Yeah, it's but before I actually talk about the sensors themselves, I would like to clarify what I mean by quantum sensors and say a few words on the landscape in which this whole thing is embedded. And then I'll spend most of the time talking about quantum sensors for low energy particle physics, and some time actually talking about high energy physics detectors that build on quantum sensors. And this is more speculative, obviously, than this part here. This is already well-established field. So first of all, when I talk about quantum sensors, one has to think of a quantum sensor as a system that can register a change of quantum state caused by the interaction with an external system. So for example, a transition between a superconducting state and a normal conducting state, or the transition of an atom from one state to another, or the change of the resonant frequency of a system, if these are quantized. And so with that definition in mind, a quantum sensor is a device, the measurement capabilities of which are enabled by our ability to manipulate and read out its quantum states. And obviously, quantum changes of quantum states require very low energies. So these commensurate energies being very low, quantum sensors are ideally matched to low energy particle physics. And I'll talk about the focus on CERN activities in both low and high energy particle physics. What I will not be talking about is entanglement. And this is sort of the most interesting part about quantum sensors, would be to see how one can bring entanglement to bear on high energy particle physics. I have no idea. So this is an open question. Really, we're trying to look at individual interactions here. The technologies that come to mind when one talks about quantum sensors are listed here. So superconducting devices, transition edge sensors, superconducting nanowire single photon detectors, cryoelectronics, the whole family of spin-based detectors or detectors for spin, such as nitrogen vacancy diamonds, optical clocks, the very large family of ionic, molecular, atomic systems that one can play with, optomechanical sensors, and finally, an equally large family of metamaterials and low-dimensional materials where engineering takes place at the atomic or few atomic scale. And with these kinds of devices, one can look at these kinds of physics, so search for new physics beyond the standard model, search for axions, axion-like particles, dark matter, but also non-dark matter, ultralight particle searches. Of course, the whole very interesting question of testing quantum mechanics itself. How does the wave function collapse? How does decoherence occur? And then tests of fundamental symmetries, electric dipole moment searches, and similar types of activities. And the reason I mentioned these 6 families is actually that within the ECFA detector R&D roadmap that was published in 2021, these were the 6 families of quantum sensors that were identified as being the most relevant overall for particle physics, where a timeline was set up for these 6 families over the coming 2 decades, where the most interesting things, for example, functional high energy physics detectors based on quantum sensors, are expected to happen on a timescale of about 15 years from now, but will require, and this is the size of the red dot, a lot of effort, a lot of R&D until one can get there. But this is not just questions of high energy physics. These are also questions of investigating dark matter, looking at the foundational questions, looking at fundamental symmetries, possibly even detecting relic neutrinos from the Big Bang.
Can I ask a question?
Of course, yes, please.
Okay, so if you go back to your previous slide, why are all the technologies geared towards only these domains in physics and not other aspects of natural sciences, maybe in chemistry? This just it's not coming from any other aspect. I just is this something that has been defined by the community, that these are the important problems to look at, both length scales and time scales wise?
So within particle physics, these are the important problems.
Within particle physics.
Of course,
right.
in a more general quest, they are also important problems, but there are other equally important problems in other fields. And of course, in those fields, quantum sensors can also start playing a role or can help answer the questions. But my focus is really as a particle physicist I will sort of forget about
Sure,
most of the other areas.
Sure, but you have things like superconducting devices,
Yes.
which are fundamentally you search for materials that would have these electron-electron correlations or something of that sort, which is also a broad-based,
Absolutely, but you'll see in a short while when I talk about them how these superconducting devices can play a role for particle physics searches, where particle physics is really a very, very large field.
Sure.
When one hears particle physics, one typically thinks of high energy particle physics. This is also low energy,
Right.
where low energy can go
Right.
down to 10 to the minus 22
Sure.
electron volts.
Sure.
For example, these axions or axion-like particles, they can be extremely low mass, can have wave functions the size of a galaxy.
Right. Okay, there's one more comment.
If I can just, sorry, not to take you away from the talk, but the Jyotishman, for example, nitrogen vacancy diamonds can give you precision measurements of magnetic field, which is probably going to change how we do NMR in the future.
Exactly, and this is something,
example.
and this is something I will talk about at one point. Obviously, if you can measure magnetic fields very precisely, you can also do electroencephalography very precisely, magnetic fields within the brain, functional MRI in a way. But you can also do particle detectors, and I'll come back to that.
So sorry. So putting the Jyotishman's question in a different way from a particle physicist, like why, we already are looking for axion or a new particle and all these things in different things, particularly the mass range that we're trying to explore. In that mass range, why these detectors are important? I thought that is probably will go in the next slide. So
indeed, I will come to that in a few minutes. But also I will
wait.
I will highlight the challenges and how one can work around the challenges, or what ideas there are to work around the challenges. Because in particular for low mass axions, one of the challenges is the sensitivity of your detector and of the technique that is being used when you use radio frequency cavities. I'll come back to that in a second.
Thanks, Mike.
So this is also not happening in vacuum. There's a quantum initiative at CERN that's taking place in a larger context also of the physics beyond collider activity at CERN, which is gathering a very large low energy particle physics community and is already trying to carry out experiments with quantum sensors, very rapidly investigating new phase space. And some of the points that I'll be touching on really have to do with how to scale up to larger systems and how to expand the explored phase space. And the technologies I'll really be focusing on for the first part, for the low energy particle physics side of things, have to do with particles, atoms, ions, and nuclei for tests of QED, searches for beyond the standard model, and tests of fundamental symmetries, radio frequency cavities for axion searches, and atom interferometers for dark matter searches, but also for other types of symmetry searches. So let me start with particles, atoms, ions, and nuclei. And here, one of the workhorses are penning traps, and a particularly interesting system that I'll just highlight. I'm picking out a few interesting topics, are highly charged ions in penning traps. So in a penning trap, any charged particle will have an axial motion defined by the electric field and a magnetic motion or a cyclotron motion that is defined by the magnetic field that is axial here. And if you measure these frequencies, you can determine a lot about the systems that you're playing with. This is for charged particles, but of course, if you don't have a charged particle, but a highly charged ion, this highly charged ion will have sublevels, energy levels. The binding energies of these highly charged ions, or of the electrons in the highly charged ions, scale as the charge to the square. The hyperfine splitting scales as the charge to the third. QED effect scale is Z to the fourth, but the sensitivity to external electric fields via, for example, Stark shifts, scales as the charge to the -6. So these are great systems if you want to ignore any external perturbation. And furthermore, these very strong field effects mean that if you compare a normal boron atom, where the hyperfine splitting between the 2p1/2 and the 2p3/2 state is around 800 micrometers, so in the far, far infrared, an analog to this system here is argon 13+, where the same energy levels can be seen, but now this hyperfine splitting, instead of being in the far infrared, is right in the middle of the optical regime of 440 nanometers. So you can bring the full power of high precision lasers to bear on measuring these hyperfine splittings, something that's very difficult to do here. Similarly, interesting developments in recent years have to do with trying to measure the electron's electric dipole moment in molecules where one has very strong electric fields, looking for a nuclear clock, thorium-229, the isomer of thorium-229 has the potential of reaching precisions of 10 to the minus 20. And also molecular and ionic clocks have not yet been explored to a very large extent. So I'd like to talk about a few systems that we're starting to play with and that have the potential to feed into exactly these questions. And these have to do with antiprotonic atoms. So with these antiprotonic atoms, we think that we should be able to produce a completely novel type of highly charged system, highly charged ionic systems. So the way you form an antiprotonic atom is by replacing an electron by an antiproton. The antiproton is captured. Then, because there's no Pauli blockades to stop it from cascading down, it will cascade down through the electrons, Auger eject all the electrons, and then end up annihilating on the bare nucleus. This annihilation removes one nucleon, a proton, a neutron, excites the nucleus only very slightly because it's a peripheral annihilation. So you end up with a highly charged nucleus, which you can then sort of dress with an electron through the form of positronium. This is something that we're already doing with anti-hydrogen production. This is something that can be easily adapted to forming then Rydberg ions. So this is then in a Rydberg state, the electron, surrounding a highly charged nucleus. So this is basically hydrogen, but it's a highly charged version of hydrogen, very simple to calculate theoretically, and with a great potential of measuring beyond the standard model effects in the system through spectroscopy. So you can, in principle, build this thing here, but you can also build this thing here, where you don't have an electron flying around the nucleus, but an antiproton. So you can build antiprotonic, highly charged Rydberg ions that remain trapped within the device in which you've made them. And this should allow you to probe completely non-standard interactions. Of course, you can do more. You can actually build antiprotonic atoms by having an antiproton in a Rydberg orbit around this system here. So you can choose your charge in a way. And you can even think of building molecules where the antiproton is then subject in a similar system as in a molecular system where you try to measure the electric dipole moment of an electron to the electric field between two nuclei inside a molecule. So you can start thinking about measuring or searching for an electric dipole moment of the antiproton. And this is the only way you can do this for protons or antiprotons. For protons, you can only do it inside an accelerator. For antiprotons, you can actually use the same techniques that are being developed now for electric dipole moment searches, which in principle should be more sensitive than anything you can do with an accelerator. And then finally, you can use these antiprotonic atoms to look for something completely different, a candidate for dark matter. This is a candidate that has been predicted or has been proposed by Glenys Farrar. It's a sexaquark. So just like you can have 2-quark, 3-quark, tetraquark, pentaquark states that have been discovered in the last decades, she proposes a 6-quark state, which with a mass that is just below the lambda-lambda threshold is stable and is a very good candidate for dark matter. The trick is to form this thing, and the way one can form it is by forming an antiprotonic helium-3 atom, which consists of these nucleons, and then annihilating, and this happens naturally within the annihilation process, a D with a D bar, a U with a U bar. These annihilations create SS bar pairs, everything rearranges, and you end up with a sexaquark particle here, recoiling against 2K pluses and a pi minus. And this kind of delta strangeness equal +2 state is a unique signature. You only have 2 charged kaons, 2 positively charged kaons, 1 negatively charged pi minus, and missing energy, a single recoil. And so if you look at the recoil mass, the missing mass that is generated in this case here, this is what that signal would look like for a branching ratio of 10 to the minus 8. And this is what the only background that we can think of looks like. There's no resonance that can hide a peak if this sexaquark would be formed. And this is a very simple experiment to do in the coming years. So now let me switch gears and talk about radio frequency cavities. Normally, when you look at radio frequency cavities, the figure of merit that you're thinking of has to do with the coupling between the axion and the photon. It has to do with the mass of the axion, the strength of the magnetic field, the volume of your RF cavity, the temperature, and the quality factor of the cavity. Axion searches have been carried out with RF cavities in this very narrow blue window, but you'd like to be able to go down to very low masses as well. Obviously, at high energy, this is where the HEP experiments will play a role. Now, any magnetic field that you measure with allows you to do an axion search, one of which is, for example, the experiment called BASE at CERN, whose goal it is to try to measure the mass, the charge, and the magnetic moment of antiprotons inside a penning trap, just like the penning traps I mentioned before. And to do this, they embed their penning trap in a very strong axial magnetic field and couple the electrodes here to an LC circuit, a cryogenic amplifier, a mixer, and a fast Fourier transform. And one of the characterization steps that they need to carry out when they measure the magnetic moment of the antiproton is the noise spectrum that they detect. If there were an axion with this particular mass, it would show up as a spike in the noise spectrum whose temperature can be inferred from the shape here. In fact, they're using the antiproton, in this case, as a thermometer for their device. This absence of a spike in their noise spectrum allows them to create a exclusion plot for specific axion masses. So this very broad range corresponds to 2.7906 to 2.7914 nanoelectron volts. It's not exactly a very broad range. It's a very thin needle. But if you want to broaden this system here, all you need to do is develop superconducting tunable capacitors. And not something that you would normally do, but for this application, it would be worthwhile being able to vary the LC characteristics of this circuit here. You need laser-cooled resonators, you need a stronger magnetic field, and a better Fourier transform. And with those changes that are being implemented now, they should be able to cover this full range here, so between 10 to the minus 7 and 10 to the minus 9 electron volts, well below what the current limits are. And this is an experiment that's not dedicated to axion searches. It's something just completely peripheral. Yes, you have a question. You wanted to make a comment here.
Please excuse me. The axion is coupling to the electromagnetic field?
To the magnetic field. To the magnetic field, yes. So the magnetic field here, exactly.
Just the standard AE dot.
Exactly. Yes, yes, exactly. Now, this is only going to be a certain narrow window, but you'd like to be able to go to even lower masses. And there you run into a problem right away, which is that if you want to have a constant figure of merit, you can see that as the axion mass goes down, in order to keep a constant figure of merit, the volume has to go up and basically match this. So you're going from 10 to the minus 9 electron volts to 10 to the minus 22. You need to increase your volume correspondingly by many, many orders of magnitude, which is out of the question. So what has been proposed, and I'll show you the references in a second, is to build resonant cavities that don't have a single resonance, but multiple resonances, whereby you then pump the axion power into one resonance, and that then drives it into the signal mode. So you have a pump mode, you have a signal mode, and the difference between these modes is the axion mass. Now, in order to create a multiple resonant RF cavity, you can think of slightly perturbing the cavity geometry, which is what the group around Sebastian Ellis and Asher Berlin and Raffaele Dagnolo have proposed, is to perturb the geometry by creating a structure here that can be tuned. A resonant cavity like this then allows you to cover the whole range from around 10 to the minus 9 down to 10 to the minus 22, as long as you have a good enough quality factor. And here they're assuming a quality factor similar to one that has already been achieved by the dark SRF collaboration, that you're cold enough and that you measure for a very long time. whether it's possible to build such mechanically tunable dual resonant cavities is an open question. And so one of the things that is being discussed right now at CERN is to, instead of trying to mechanically tune these cavities, is try to build an RF cavity where you have a superconducting coating that you can then electrically tune, so that you generate two modes that are slightly shifted in frequency electrically rather than mechanically. That seems to be more straightforward in a certain way. And then the third topic I'd like to quickly touch upon is atom interferometry for particle physics. So here, what one is really looking for is searches for topological dark matter and ultralight dark matter, but also symmetry violation searches like Lorentz invariance violation or position invariance. And obviously, all this is driven by the wish to have a gravitational wave detector in space. And just to give you a cartoon picture of the sensitivity of an atom interferometer compared to the best electrostatic accelerometers that are available now, these two images of the height sensitivity of the Earth with these two detectors will allow you, of course, to be much, much more sensitive to minute variations and be less sensitive to noise across the whole bandwidth. And this is something that's being worked on both in Europe and the United States, ION in the UK, MAGES at Fermilab, but also in China and in France. And the challenge right now is to go from a lab scale, tabletop scale device, which is in existence. For example, ION has half a dozen of these spread around the UK, to a 100-meter scale device, and then to a kilometer scale device. And this is why there's an effort ongoing right now at CERN, trying to see whether one can use the vertical shafts that are available there, together with the infrastructure. You need cryogenics, you need vacuum, you need complexity, to be able to see how one can scale from these small scale devices to larger scales. In parallel, trying to see how one brings these kinds of atom interferometers into space is taking place right now in the coming years. There are Pathfinder technology development missions scaled for around 2030. And the goal is then to take these large-scale systems into a multi-satellite spatial atom interferometer on a time scale of about, well, 20, 25 years from now.
I'm really sorry, Michael.
Yes.
Just to keep interrupting with it. The basic idea is, so you have this topological dark matter, which is some very long wavelength excitation.
Yeah.
And then you have these different clocks, let's say, or atoms. And
Yes.
You compare the time keeping and so on.
In a way, it's that if you think of a gravitational wave, it's sort of the same thing, because what you're doing is you're perturbing the geometry locally. And so the interferometer tells you what the local space-time looks like. And that's basically what you're measuring, but at different points. And if you can build a plane of 3, then you have basically a sensitivity in that plane. You build a larger number of satellites, you get sensitivity to topological defects going through the Earth or through space from different directions. So that's all I wanted to say about low energy particle physics, because although there are many, many ideas, I don't have time to cover them all. My background is really high energy particle physics, and this is also where some of the groups that we're in touch with are probably going to be impacted. So I'm going to switch to high energy applications of quantum sensors. And as you can see, this is very speculative. I give a warning here. And the warning is not random, because most detectors in high energy physics rely on a large number of interactions between a particle and the detector. So large numbers of electrons, which is sort of the opposite of what a quantum sensor does. A quantum sensor is a single state, a change of state from one state to another. Now here, instead of using the quantum sensors as quantum sensors per se, you rely on them that in a way that they can help enhance properties of existing detectors in such a way that you can measure things that are not measurable currently, or you measure them better than they can be measured right now. And of course, the main focus, this is given by high energy particle physics, is on tracking, calorimetry, timing, novel observables, and pileup reduction. So concepts that are very close to the heart of particle physics detectors. And these ideas are ideas, not more than that. Now, if one puts this into the context of these families that I talked about before, low dimensional materials and nano-engineered materials have quite a few possible applications. Atoms, molecules, ions also have some. I'd like to come back to those as well. Spin-based sensors are going to possibly play a role for a new type of detector, a helicity detector, and superconducting sensors can actually play a role via their quantum nature of transitions, quantum transitions. So let me start with the simplest system, quantum dots, very small crystals with a small number of atoms with specific geometries. And these are under study right now. For example, cesium lead bromide or zinc oxide gadolinium. And the nice thing about these small crystals is that the scintillation light that they produce is very fast. The rise time is well below a nanosecond, but also the decay time. If you look at the decay curve here, you see that there's a component that has a decay time of 43 picoseconds, another one of 350 picoseconds. So these are sub-nanosecond decay times, which is of interest when you're trying to differentiate one event from another one. And this is not just this specific cesium lead bromide nanocrystal. It's a characteristic of all perovskites. This ZNO gadolinium has a decay time of 210 picoseconds. So these are incredibly good decay times. The problem is that they don't produce very many photons. So the light yield is not yet where it should be. You need many, many photons to benefit from this very rapid rise and decay. And that's an area where having a denser material, even monocrystals of perovskites, is something one has to think about and it should work on. But there's another aspect to quantum dots, which is their chromatic tunability. So I mentioned that the properties change depending on the size of the quantum dot. Here, this is really an illustration of what is happening. Very small quantum dots will emit light in the blue. And as you go to larger and larger quantum dots, the emission spectrum moves to the red, which means that you have chromatic tunability just by choosing the size of your quantum dots, which means you can optimize, in principle, the scintillating light that you produce to the quantum efficiency of the photodetector. So they're fast, they're optimizable wavelength shifters. And if you deposit this on the surface of a high Z material, you basically get a visible light wavelength shifter with whatever color you want. You can also think of embedding this in a high Z material or making the calorimeter itself out of the perovskite material. So for example, a two species mix of nanodots and microcrystals of lead tungstate inside a polymer matrix, that would produce a continuous or quasi-continuous visible light emitter. And so the obvious question is, what happens to the light that you emit? Does it get reabsorbed? And that is something that is very nicely tunable as well. So here are some specific types of nanodots. These are triangular carbon nanodots. And if you look at these individual nanodots, their emission spectrum under illumination by UV light is extremely narrow band. The width of the emission spectrum is about 20 nanometers, which means that if the photons that are emitted here would then encounter other nanodots at some other point, only if the spectrum has an overlap at within that spectrum here would they be absorbed again. And if you look at the absorption spectrum of these nanodots, they're well separated. They're separated by more than the bandwidth, the emission bandwidth of the nanodot itself. So any emitted light is not going to get reabsorbed by the same nanodots. And you can then take this idea one step further by building a calorimeter where in the different slices, you deposit nanodots of a specific type. Here, for example, nanodots that absorb UV light and emit red light of 598 nanometer. This 598 nanometer light will no longer be absorbed. It cannot be absorbed again. It'll propagate all the way to the end. You do the same here with a red, yellow, green, blue, dark blue, or violet nanodot emitter. And in each one of these, any light that's produced will propagate until the end of the crystal, where you can place a spectrometer and then measure the spectral intensity as a function of the frequency, which means that, for example, if a particle deposits energy inside a shower, inside this chromatic calorimeter, the intensity profile here, the chromatic or spectral intensity here, will tell you the exact shower shape. And that allows you then to differentiate different types of particle interactions.
I have a question
Yes.
here. What kind of interaction is happening with the particle coming in? And because these are all photon activated. So what
Yeah.
you
So this
yeah.
is where
could you explain that?
there's a step that I sort of glossed over. It's this one here. What you do is that these nanodots are triggered by UV light. The UV light that is produced by the interaction of charged particles inside your calorimeter is what
Okay.
gets the nanodots to
Okay.
get excited and then fluoresce in the visible range.
So you get UV radiation because of the particle interactions.
Exactly. So the primary particle interaction generates UV light,
Okay.
and that's what you see then.
Okay, so that is a secondary detection in some sense of the
Yeah.
particle.
It's
That UV
basically a
light, yeah.
continuous wavelength shifter inside your calorimeter.
Got
That's
it.
basically what it is. So instead of having just a green wavelength shifter out here,
Sure.
you embed it inside the calorimeter.
Sure, thank you.
So this is just passive quantum dots. They don't do anything else but act as wavelength shifters. They cannot be amplified. They're there, they have their properties. You cannot change them. You cannot turn them on or off, and they cannot be modified. But you can imagine the possibility of having active scintillating materials, which are amplifiable or modifiable, which you could even pulse or prime, and where you could adapt the gain in situ, for example, to the radiation damage that accumulates over time. And what these things are basically quantum dots of the type of gallium arsenide, indium arsenide mix. These things here can be built. If you look at these different types of quantum dots, they're formed depending on the mixing ratio between these two types of compounds. And the emission spectrum then depends on what you're looking at. The quantum dots emit typically in the far infrared, the quantum well dots in the near infrared, and the quantum wells in the very near infrared. The decay times for the quantum wells are very long. This is 50, 60 nanoseconds. So they're not necessarily an interesting type of quantum dot to be focusing on. But the quantum dots themselves here, these that are up here, they have a relatively rapid decay curve. And these rapidly decaying quantum dots are active. This is an active material. And furthermore, the wavelength that they emit of somewhere between 1200 and 1400 nanometers is in an area where silicon itself is transparent. This is something I discovered that everybody knows, but I didn't. Silicon is completely transparent in between 1400 and 1800 nanometers. So you could imagine putting these kinds of quantum dots inside the tracker, and you would still get calorimetric information. The photons would propagate through your silicon tracker to outside photodetection. Something to think about in terms of the geometry of the detector that one would build. Furthermore, these quantum dots are radiation resistant. There are measurements that have been done that show that they are radiation resistance to a certain point. Whether they can survive the kind of fluence that you would get for an inner detector inside the LHC or the high luminosity LHC, that remains to be tested and shown. One has to see. This is not something that can be predicted right now. But these are sort of semi-active scintillators. But you can go one step further and combine. So as again, this is all hypothetical, speculative. I don't know that this would work. But you can imagine combining a standard silicon detector where you generate many, many electrons to a quantum cascade laser where a single electron enters and drops through well-defined steps, and at every step emits a photon corresponding to the energy difference between the electronically defined steps. So inside such an active region, you have constant electric fields between the layers, and these infrared photons then correspond to a single electron. Now imagine you don't have a single electron, but the large number of electrons that you get from ionizing radiation, you should be able to produce a vast number of infrared photons. Infrared photons means that you then have to be able to detect these infrared photons. So this is something that is challenging. These are terahertz photons. So you have to be able to have a photodetector that works efficiently in the terahertz regime, but then that would then be tunable, which is a great advantage. So R&D here might be worthwhile thinking of.
Can I ask another
Of course, yes.
Interesting ideas. the one that you said previously for the quantum dots,
Yes.
for example, you had said, some wavelength range in UV, say 365 nanometers you showed for one of these materials. But what is the range of wavelengths that you get from these particle-particle interactions in UV? What is the subspace of radiation
So
coverage?
for a primary particle going into a scintillator, you will get a large bandwidth of UV light.
Yeah, so can it be like at 200 nanometers?
Yes, absolutely, yes.
So would that lead to electron generation from these?
Absolutely.
materials?
Oh, absolutely.
That would be helpful here, I guess.
So the electron generated inside a calorimeter,
Right.
depending on the energy of the interaction, will also then radiate themselves. So you get a whole cascade, a sort of electromagnetic shower, which is what you basically saw as this curve. This is the shower profile that you might want to be able to measure. So from zero-dimensional materials to two-dimensional materials, these are now monolayers of graphene. They're being studied right now at CERN for two applications. Let me start with this one here, with the amplification first. One of the things that you would like to be able to tune is inside drift chambers, separate the detection region from the amplification region. And this is done by a very thin mesh of relatively large holes of a few micron size, where you have a very well-defined electric field. Now, the problem is that inside the amplification region, you basically accelerate the electrons through a very strong electric field. They undergo a shower process, and this shower process then generates enough electrons that you can detect them. That's the good side, but it also leaves behind a large number of ions that will drift into the detection region and poison the detection region, because they will basically eat up any electrons that are flying around. So you'd like to be able to separate these two regions, and this is where graphene can come in. Graphene, to cover up these grid holes, is being looked into, because if you look at what can go through graphene, electrons are able to pass through a monolayer of graphene with an efficiency of around 99.9%. Very, very transparent to electrons, but ions should not be able to pass through. So a monolayer of graphene would be great. The trick then is how to apply a monolayer consistently over large areas. So this is a big challenge. The other similar application has to do with work functions of the detector for the electrons. And the number of monolayers of graphene, so one monolayer, two monolayers, three monolayers, four monolayers, will change the work function of the electrons coming out of this material. So again, you want to have a very good control of how many layers of graphene you deposit. That then allows you to fine-tune the work function of your photodetector. Coming to atoms, this is the same thing I just mentioned, an active drift region and then an amplification region. And I just explained why one would like to separate these two regions from each other via a monodirectional membrane. But you also can play with another effect that is happening in here. These showers that are produced by accelerating the electrons between the grid here and the detection plane have to do with the ionization that the electrons that are being accelerated can achieve in the gas, in this amplification region. Now, if you're able to reduce the threshold for ionization, you can produce more electrons for the same electric field. So just prior to having electrons drift in from the drift region, you can try to excite the atoms in this area here into a Rydberg state, a highly excited state, in which case their ionization energy is dramatically reduced. From a particle physicist point of view, it's as if the dEdx, the energy loss, has been increased dramatically. It's equivalent to that, except that you've done this by priming the atoms in this amplification region. That leads to an effective reduction of the ionization threshold and thus to a higher electron yield. So either you get a bigger signal, or you can work with a lower acceleration field here, which means that you will have less of a problem with pollutants, the ions that are produced in here, drifting back into this region. So you can play it both ways if you can manage to excite a reasonable fraction of the atoms here into Rydberg states. And you can play the same game, not just in the amplification region, but also in the drift region itself. Let's say just before you have a particle collision in the middle of this time projection chamber, this gas drift chamber, you excite the atoms into a low-lying state, not all the way to the ionization threshold, not a slight bit below, but halfway up there. then any particle, any charged particles that are produced inside this through a collision of two particles hitting each other here in the center will be able to excite these atoms even more. They're already excited, you can excite them even more, or you can ionize them through the secondary particle here. And you can then, even with a second pulse, laser pulse, ionize those that are highly excited, while leaving the ones that are not affected to cascade down back to the ground state. So a Rydberg atom TPC is what you would end up having here. It's a complex set of atom excitations, collisions, photoionization, and drifting of the electrons in. It's not a high rate detector. Yes?
Yeah. These are extremely susceptible to electric fields.
Of course, absolutely.
Would this be highly noisy?
It depends how you build it and at what level you excite the atoms in here. If the atoms are excited into, say, n equal 5 or 6, they're not very sensitive yet. The only noise you would get is if the electrons then come out. And for that, you need an interaction with a charged particle.
Okay.
The photons for the photoionization, or the wavelength, is chosen such that from the level of 5, you cannot photoionize. If the particles that go through excite from the level of 5, n equal 5 to n equal 20, then you have enough energy with the photons to photoionize them. So I don't think that noise, electron noise, would be a problem in terms of electrons being produced. What will be tricky is probably how all these Rydberg atoms, that are, after all, quite large objects, will fit into this volume, because there are Rydberg blockades.
Yeah.
And so at some point, you're not going to...
Yeah, Rydberg blockade is a serious question, I think.
Yeah.
Can actually
Exactly. So that's something, okay, so partly is an experimental question, partly it's not really a problem either, because as long as you get a bit more electrons out, you've won. And so I don't think you'll actually excite all the atoms in this volume here into Rydberg states, maybe only 10%, but those 10% will give you more electrons than the primary ionization, because for primary ionization, the charged particle that you're interested in has to pass quite close to the atom to ionize it. But if you have a Rydberg atom, this exact sensitivity to external electric fields means that you should be able to ionize even for very peripheral or remote interactions.
Exactly.
So one has to see how this could work.
Sure.
Okay, then spin-based sensors. This is something we discussed over lunch, how we could use quantum systems to measure magnetic fields. And one of the areas in which this is being done is in nitrogen vacancy diamonds, where you can probe the external magnetic field, the effect of an external magnetic field on the states, the spin states, or the energy levels of a single vacancy in here. Now, you can also turn this on its head, and this is where it gets interesting, because this is something that has already been proposed for marker molecules. So this is not particle physics. This is in a totally different area where you'd like to have spin polarized marker molecules. And the idea is that you spin polarize the nitrogen vacancies through microwaves, and then that polarization propagates to the surface, where then collisions between the marker molecules and the surface of the nitrogen vacancy diamond, the polarized nitrogen vacancy diamond, then leads to a stream of spin polarized marker molecules. Now, this is very nice, but we can take this another step further. Imagine now that instead of having just a nozzle here where you create polarized molecules, you actually create a whole plane of polarized crystals, of polarized nitrogen vacancy diamonds. You polarize this guy through something called hyperpolarization. This one here polarizes a number of atoms around it. And so any scattering that will happen between a primary particle and this ensemble of polarized atoms leads to spin-dependent scattering, which means that if you have several polarization planes embedded between trackers, measuring the scattering angles should allow you to reconstruct the helicity of the initial particle. And barring decays of a particle, where you can actually measure the angular distribution of the decay particles and extract what the helicity of the initial particle was, I don't know of any way to measure the helicity. This would be a way to measure helicity of a single particle. One caveat, right now, you get about 10 to the 16 to 10 to the 18 nitrogen vacancies per cubic centimeter. Hyperpolarization fills around a factor of 100 more atoms around each one of these. So you end up with about 10 to the 18 to 10 to the 20 polarized scatterers inside 10 to the 23 atoms, which means you have a polarization of 1 per mil, which is lousy. So you need to bring this up by a factor of about 10 in every direction.
How fast will be these detectors depends on the polarization timescale transfer,
Yes,
right?
yes.
So what timescales are these? And these polarization transfers happen from the NV center to the
To these here,
yeah.
what you're trying to think about something that is long-term. That's not something that you
Okay,
do on a
so
particle to
so
particle.
you're going to average over a long time. Okay.
Well,
Because the
this
particle-
polarization is something you build up over time. You want that to be there all the time.
Okay.
So you don't
okay.
care what happens in the first 2, 3, 10 collisions.
Okay.
It's once this hyperpolarization has taken place, then your polarized plane is really polarized. It
Okay.
stays polarized.
Okay. Okay.
And probably you have to repump. This is something I don't know, but
Sure.
probably you have to repump your microwaves continuously.
With the microwave continuously
Yeah.
switch on. Yeah.
Okay, now these are all detectors that use effects that have to do with quantum systems, quantum state changes, but only in bulk. And so it's not really a quantum sensor per se. Right? This is a quantum sensor where if you look at what single superconducting nanowire single photon detectors do, is they go from a superconducting state through the absorption of a photon into a normal conducting state. This state, this region grows over time and then diffuses, cools down, and goes back to this state. So you end up with a voltage pulse that has to do with the absorption of a single photon. Now, of course, a single photon or a minimum ionizing particle will behave the same way. A MIP that goes through here will have the same kind of pattern. What is interesting to consider is that a normal minimum ionizing particle deposits around 20 kiloelectron volts per 100 micron of thickness that it traverses. These detectors here are currently sensitive at the 100 millielectron volts per 10 micron, and the hope is to go down to 12 millielectron volts per 100 micron. So there's a factor of 10 to the 6 between these here too, which means that you should be able to be sensitive to an energy deposit that's 10 to the 6 times smaller than that of a minimum ionizing particle.
Just a quick question here. So yes, you're absolutely right. The 20 kV per 100 micron, but it also depends on what the noise is. So
Of course.
what kind of signal? So like in current MIP detectors we are dealing with, let's say in CMS,
Yeah.
depending on the gain of your electronics, we can easily have signal to noise of 15, even with those parameters. So what kind of signal to noise are we talking of?
So for these guys here, this is really the level, the energy threshold that you're working on. So this is where the noise is sitting, 10 millielectron volts per 100 micron. So these are really, really very low noise devices. They're basically quiet. Anything that deposits more than 20 millielectron volts will show up as a signal, as a real voltage pulse. You have to think of your floor being here about 10 or 12, and a signal that goes above that floor by 20, 30, 40 millielectron volts. So the factor of 10 to the 6 sensitivity is really there. Maybe it's 10 to the 5, but that's where there's a huge gain. And now, if you have that kind of sensitivity, you could think of building an array, a stack of individual pixels made up of these. So a transition edge sensor in form of an array, and you stack these arrays, one above the other. You put this whole thing inside a veto box that will detect any minimum ionizing particles as they go through from here to here. And then you look for signals inside this device. A minimum ionizing particle will show up here, in here, of course, because these all flip on from superconducting to normal conducting, and then back here. But a very low energy depositing particle, a millicharge particle or a microcharge particle, will not trigger anything out here, but will trigger the individual bits in here. So you get a tracker, a tracking detector, which allows you to reconstruct the trajectory of millicharged particles, of hypothetical millicharged particles. In a way, this is a challenge to the theorists. Are there any valid candidates that would that would make it worthwhile trying to build something like this?
Yeah, I recall that this has been used in astronomy for low light level detection.
Yes, exactly.
You are aware of this?
Yes, this is exactly where the idea comes from. These transition edge sensors, arrays, they're currently flying. They're all over the place.
They're all over the place, yes.
And they measure infrared photons or
So
far infrared.
what's the experience from there? That what kind of noise levels are they?
So the noise levels there, you have to be careful. Of course, you're going to get single electrons. In space, you're obviously going to get electrons occasionally. What you need to do for this here is to avoid that an electron that is produced by a scatterer then goes through this detector and shows up as a track.
Yeah.
But you can do that because these electrons are relatively low energy, so you can sandwich these arrays with absorbers, lead absorbers. That means any electron that's produced somewhere else gets stuck before it goes from one plane to the next.
Sure.
So the experience with the noise of these TS arrays in space is excellent. They're beautiful detectors for infrared astronomy.
Would you trying to shift the regime to particle detection?
To particle detection, yes. To the detection of hypothetical particles.
Sure. Thanks.
And these are very thin detectors. They have a thickness of a few tens of nanometers. So you can think of having this stack actually also looking inside a active target. You shoot a beam into a stack like this, a charged particle will of course go through and show a signal, but a neutral particle will not. A neutral particle will go through, might decay a little bit later, and you should be able to see decay lengths at the level of something like tens of nanometers, whereas normally decay lengths are in the microns, tens of microns, hundreds of microns. So this might, and again, theoretical guidance is welcome for this, enable looking for particles that one hasn't been able to differentiate from charged particle decays currently. I'm not so sure about this one. So with all that in mind, I'd like to fit this back into the roadmap that we're currently working on for the next decade, basically, on these 6 families of detectors, all of which have a very active application right now, but also a very, very promising future in terms of the phase space that can be explored, in some cases 5, 6 orders of magnitude beyond what is currently possible in terms of sensitivity. And that's something that's going on this year, right now. We're implementing this roadmap and trying to build a collaboration to work on the technologies that will enable it to build new experiments. So I think with that, I've come to the end of the talk, with the exception of this timeline, which might be interesting more for not physics detector discussions, but planning discussions. We're right here. We've been talking to interested parties, or we are in the process of talking to interested parties. We've identified a number of conveners for individual families of these quantum sensors. We've also asked for projects to be sent to us if people have ideas of what kind of technologies could be interesting to work on. We'll have a workshop among this community here by April, just before Easter at CERN. Then we want to prepare a letter of interest to be submitted in summer to CERN's detector R&D committee. Then have a conference in September, October, a sort of town hall meeting to have a wider community involvement to see which of these many ideas that we have identified here are actually going to fly and that people would be willing to work on, and then prepare a proposal for the end of the year to be submitted again to this same committee. And of course, I'll be happy to tell you a lot more about this stuff, but it's just that this is going on right now. And thank you for your attention.
Thank you, Michael. That was wonderful, covering a lot of space and time. So you want to ask? Yeah, questions.
Very quickly, 2 questions. One on the atomic interferometry that you showed, MAGIS and the other ones. So people have been doing atomic traps for quite a long time.
Yes.
What is the principal challenge that ultimately it would take a lot of time to build large scale? So how do you physically launch the atoms and then bring it back?
One of the challenges has been to standardize the infrastructure. So if you look at what was done in the ION collaboration, or in the ION effort, they've looked at how atom interferometers are built. And it's typically a professor or 2 with her students working on it for 3, 4, 5 years. And then the next group comes along and reinvents the whole thing again, does it in a slightly different manner, and so on. What they've done is brought the fabrication technologies of particle physics, labs, big labs, mechanical engineers, standardized fabrication technology, and now they churn out these atom interferometers about once a month. They can deliver an atom interferometer, a working system, within about 3 months from the moment that they start on it. And they can do several in parallel. So there are half a dozen now in the UK, all of them turning on one after the other. So you get a network right away. Now, scaling this to a larger scale is not obvious. You discover the problems that you have then in going to larger volumes, because what you really want to do is launch your atoms to a very high height. And so what is your sensitivity if you launch over this distance or if you launch over 10 meters? That's one of the things that you have to discover by just trying to build such a prototype. And then improving on it, and then going to the standardization step again. So already the interesting thing there is that as you go to build a better device, your reach already now increases significantly. So you can already do physics while you're working on the technology.
Yeah.
Quickly, one more question. This is on what I agree you gave the caveats on the calorimetry applications, but I just wanted to play devil's advocate for the very nice idea that you mentioned that with the crystals where you could have readout with different colors.
Yeah.
So I guess the nice thing is you can embed these things in a homogeneous crystal. So that's why you get a very nice stochastic term. But then you also want to build a very granular detector. So so how would you fit enough photo detectors at the back of the crystal to read these
You've
colors?
put your finger on the sore point, because of course, if you need a spectrometer that's this size and your crystal is this big, you haven't actually won anything. So there are two approaches that I would think should be looked into. One of them have to do with, again, metamaterials, nanostructured materials, where you can create optics in a very thin layer that have very nice tunable, designable properties. So you can think of having a prismatic setup on a monolayer or well, de facto monolayer within a few micron. That's one approach, and one has to look into that, and then you'd have a small band of photodetectors. The other one is something that already exists. I didn't show the slide, but I will show it on tomorrow for the students, and that's to use a real prism, but then to measure the photon energy by looking at where it hits a nanowire, superconducting nanowire, and depending on where it hits. So the position then maps to the energy, to the Bragg angle that you're looking for. And if you have a low enough number of photons, you can repeat this many, many times. So having a superconducting nanowire as your detecting plane, and then all you measure is just the arrival time of 2 pulses, that tells you already what the photon's energy is.
You can still build large nanocrystal arrays.
Yes.
That's possible.
Yeah.
The lead, cesium lead iodide material.
Yes.
You can also, don't have to have single crystal.
No, exactly. They can be small monocrystals because I don't really care about their orientation.
Absolutely.
Yeah.
Yes. Thanks a lot for a wonderful talk spanning so many developments. I just want to go back to the beginning of your talk, if I may. And you mentioned that, and it's true, none of what you described and much of what goes on in the name of quantum technology doesn't actually use entanglement, and yet allows us to go, as you showed, very far. But of course, entanglement is one of the truly magical things about quantum mechanics. And I was wondering, just as for quantum computing, where at least theoretically we know we can build error correction thanks to entanglement, have people thought about it, say, in particle detectors and so on?
So in particle detectors, to my knowledge, not at all. I mean, high energy physics detectors. In low energy particle detectors, I think you just need to talk to Cinzia, who uses correlations maybe more than entanglement, but certainly already the quantum nature of the photons.
There are other applications. Well, there are, of course, entangled states.
Yes.
That we know in particle physics are there. So some of the decays and kaon decays.
Yes, of course.
Decay of positronium, for example, with the 2 back-to-back. Those are entangled states. So there are many applications which are using them. But then it is true that finding really a detector that within the type of multiplicity that we observe in particle physics would take advantage of that.
It's
is not yet.
no, nobody.
I think I know that people are thinking about it.
but I'm not sure that we are there
Yeah.
yet. But for other applications, yes,
Yeah.
for sure. There are, of course, we have optics and quantum optics, quantum imaging, and now this is also getting to the regimes of X-rays. And this is, yes, something that I'm working on. Sorry, something that I'm not working on. And for the people online, I'm sorry they didn't hear what I said before. So it's a field which is going to grow extremely rapidly.
So in a way, it also has to do with where do you define the edge between low energy particle physics and high energy particle physics. For me, it's at about a keV. So X-rays are already on the high energy side.
Yes.
Thank you.
Okay, so thanks for a very exciting talk, particularly the topic. I think you talked about these nano scintillation crystals, right? This is cesium lead bromine or something like that. These are very new, I mean, in the concepts, right?
So
I want to know what is the quantum efficiency of such things. I mean, how many visible photons produced per MeV deposition of energy?
This is exactly the problem that one has to look into, the light yield. What is the light yield of these very small crystals? It's lousy.
What's the number? I mean, that's
I don't even know a number, but
30 to 40%.
yes, but
Nowadays
if you have them in bulk, yes,
no,
yeah.
the nanocrystal.
yeah, but I'm thinking in terms of, you know,
Yes.
it's the relative density of the nano dots compared to the rest of the calorimeter. So that's something that has to be, if you salt the,
So do you have a number? I know what is sodium iodide. Let us say 37.
Yeah, yeah.
It's a number of photons per MeV deposition, per mega electron volt deposition.
Mentioning about the UV excitation.
Okay.
Yeah.
And these are those band transitions, not molecular excitation like organic crystals. These are really in the band. This is we are engineering, and it is in that forbidden band. These transitions.
So the engineering aspect is being able to choose your material, to choose your geometry, and to choose your size. And you have 3 knobs on which you can turn, which is a lot of freedom then. I don't know if that's enough then, of course, because you may hit walls, other walls. These carbon nanodots, for example, they're just carbon atoms stuck to each other. If you expose these to a high radiation environment, I would expect that individual carbon atoms come off so that the geometry doesn't stay stable, so that your narrow bandwidth emission spectrum over time broadens. I mean, just guessing, but that's what I would expect to see. So that's probably not a good example, but maybe other molecules or other structures are better.
Thank you.
Hi. For the spin-based detector that you mentioned, does it require the angular distribution for many events, or can it? Can it detect the helicity of a single event, like for unpolarized particle decaying into some particles? Can it? Is it possible to say what is the helicity of the final state particle?
So you're asking about the helicity detector.
Yeah.
The model that I'm presenting here assumes that you don't have a polarized source. So your initial particle is completely unpolarized. You just have a polarized target. This is very similar to what happens if you have a beam impinging on a polarized target. Then the polarized target acts as a spin filter in a certain way. Now, how well this works, I don't know. I cannot say. That's something that I can only throw out as a suggestion to look into.
Okay, so in principle, for every event, we can say the helicity of the final state particle.
That would be the dream. That would be the hope that this kind of approach might lead to being able to measure for each individual particle in a collider its helicity. Yeah.
Okay, thank you.
Thank you. Any other questions? Well, if there aren't, then let's thank Michael once again for a wonderful talk. I would request all of you to move to the snacks area, which is outside the canteen. We'll have some tea and snacks arranged for you. So thank you very much, Michael. This was fantastic.
I'm glad that.
And you did it on time. It was all going to be done.
Okay.
With all the questions.
Wonderful.
So very nice talk.
Yes, nice to see you again.